Before we go over the sketch of the proof on 4.4, let's look at conditions for a zero determinant. So it's kind of a theorem, but we'll just go over properties. So this theorem is called conditions for zero determinant. So if A is a square matrix, then the determinant of A is equal to 0 if and only if 1 an entire row or column is 0, which that should be obvious. Expand on that row or column. 2, two rows or columns are equal. Okay, so that you basically just do an operation on those to get a zero row or column, and then it kind of works out. And then 3, one row or column is a multiple of another row or column. So one row or column is another multiple of a row or column. So those are the three main things to see. For example, let's take a look at this example. So find the determinant of this without actually taking the determinant. So if you just saw something like this, 4, -2, 0, 6, 1, 3, 8, 5, 7, -2, 1, -6, and -2, 1, 0, 3. Not completely obvious at first, but if you look at, just going to change colors there. If you look at row 1 and row 2, then, oh, it's supposed to be negative. Then you can see that row 1 and, I said row 2. So row 1 and row 4, 1, 2, 3, 4, are a scalar multiple of each other. So basically all you'd have to do is factor out the scalar multiple, and then you end up with two rows that are the same, which makes sense. So if you see that, then you know the determinant has to be 0. Okay, let's go back to the sketch of the proof of theorem 4.4. So let's just go ahead and copy this theorem, bring it down here, and let's go through that proof. So not complete because it's a lot of little details, but let's take a look. So first, let's suppose so you have two matrices, A and B, square matrix, and it's not assumed that they're invertible, but we'll just look at the invertible case. So look at the book. So first, suppose you could call this a lemma. It's like a lemma is what's used to prove the theorem. So this is we'll call this lemma 1. There's not 2, but we'll just call it lemma 1 anyway. Okay, so let's assume or suppose first that A is a diagonal matrix. So we know a diagonal, the determinant of a diagonal matrix is the product of its diagonals. So if it's a diagonal matrix, then the results is pretty clear. B is just some matrix, and say it's an invertible matrix as well. So what you get is A11 on its diagonal, and then all the way down to ANN. And then in the book, you'll see that they put big zeros here to indicate that it's a diagonal matrix. So that's A times the matrix B, B11, all the way to B1N, BN1, and BNN. Without putting in anything else, that's how you can write the matrix. So if you look at the determinant of that whole thing, then you can picture the product of this going into each row. So this diagonal will be a product of each one of these rows. So what you end up doing, so if you picture it like that, for the matrix B, right? So this is my diagonal matrix A, and then my matrix B. So you use the scalar multiple property of each of the rows. So you use or apply the scalar multiple property of each row. So then you get, if you do that, then you get the determinant of AB is equal to A11, A22, etc., all the way to ANN times the determinant of B. And then we know that the determinant of a diagonal matrix is the product of its diagonal. So that's just going to be the determinant of A times the determinant of B. Okay, so we're going to use that concept, we'll call it lemma 1, in the sketch of the proof. It's a pretty good sketch, but still a not complete proof. So now we're going to assume A is invertible. Not diagonal, but just invertible. Okay, so this is the idea or sketch, we say, of a proof. So let's assume A is invertible. And so if A is invertible, we're going to reduce A to a diagonal matrix without changing the pivots to 1. So reduce A, I said diagonal, assume A is invertible. So yeah, so reduce A to a diagonal matrix. So with row operations without changing the diagonal to 1. So we're not going to scale it. So A, we're going to reduce to the diagonal matrix D, where D is a diagonal matrix. So you do that by elementary row operations. So we do by elementary matrices. So D is going to equal E times A. So where E is the product of elementary matrices. Okay, and so it's the product of elementary matrices corresponding to the row operations used to reduce A to D. Okay, and I won't write that part down, save some little time. So it's picture E1, E2, E3, E4, and it's that product. So then what you get is that the determinant of A is equal to negative 1 to the R times the determinant of D. So that's E. You get E where R is a number of row interchanges, where R is the number of row interchanges. So you have to picture what's happening with E. That's so you're getting it to be when you interchange the rows, you end up getting a negative 1. So you do that R number of times. Okay, so determinant of A can be reduced to that because of the property of the elementary matrix. So A times B can be reduced like this. So it's E times AB. By associative property, you get EA times B, and EA is the matrix D times B. Okay, as we wrote above. So now we're going to basically put in the determinant of that. So thus, the determinant of AB is equal to negative 1 to the R times the determinant of D times B. But the determinant of D times B is a diagonal matrix. So now if we apply lemma 1, we just did, you get this is equal to negative 1 to the R times the determinant of D times the determinant of B. But we can see that this from above is the determinant of A. So that's essentially by lemma 1. And so then this equals the determinant of A times the determinant of B. Which is what we wanted to prove. Right? So if you can break up a determinant essentially individually. If you want to get into the details more, you got to say let's not assume A is invertible, and we assume A is singular, in which case you get determinant 0. So if one of these is 0, the whole thing zeroes out. There's a few more details to that, of course, but that's the idea. Okay, the other thing I want to go over just briefly is equivalent conditions. So because of the determinant and invertible, we're adding to our equivalent conditions. So this, we won't go through the proof of anything, of course, on this, but this is the following are all equivalent. We're adding to this. So let's let A be an n by n matrix. Okay, then 1, we have A is invertible. So if A is invertible, you get that the system, or the equation, AX equals B, it is the system, so AX equals B has a unique solution. And then 3, the homogeneous system, AX equals 0, has only the trivial solution, has only the trivial solution. And then 4, A is row equivalent to the identity matrix, which is right, it's because it's invertible, right? That kind of makes sense. A can be written as a product of elementary matrices. Okay, where E is elementary matrix. Okay, and then we have 6 now. So those we've all had in the past. So now we have 6 is determinant. So the determinant of A is non-zero. So that's the last, so that's adding to our equivalent conditions. So just a quick example of this to show or look at if it has a solution, you can use that property. So does the system have a unique solution? Suppose you had 2x, this is of course a simple example, but you get the idea. 2x minus 4y equal to 3, and negative x plus 2y equal to 5. So here's our system, and so that's of course in the form ax equals b, where A is that coefficient matrix. So A is equal to 2, negative 4, negative 1, 2. And if you take the determinant of A, you'll get 4 minus a negative 4, which is 0. So you get the determinant of A is equal to 0, therefore no unique solution. So answer is no. All right, so you can, it's another way to determine if a system is solvable or has a unique solution or whatever. You can analyze the system as well. I mean, this one's a simple case, but it gives us more tools to prove and show stuff in the future. All right, I think it's time to go on to the next section.